Good day everyone, I am Mary Jane Adja. For this presentation, I'll be talking about a rare event where a volcanic eruption triggered a meteotsunami in the Indian Ocean. This is based on the research article by Anup and his team published in 2024. I found this study fascinating because it showed how volcanic and atmospheric phenomena can unexpectedly affect sea levels far from the eruption itself. Tsunami are often associated with earthquakes, those dramatic undersea shocks that send waves racing toward the shore. But there's another kind, meteotsunamis. Before we get into the main event of this study, let's first understand what meteotsunamis actually are. These are sea level oscillations that happen at tsunami-like frequency, but unlike seismic tsunamis, their source is in the atmosphere, not in the earth crust. According to Anup et al. 2024, this can be triggered by things like fast-moving squalls, gravity waves, or sudden drops and rises in atmospheric pressure. Now, what makes them dangerous isn't just how they start, it's how they grow. When these waves enter certain coastal environments, especially narrow bays or steep slopes, they can resonate and amplify, turning what started as a small wave into a big coastal hazard. So even if they begin with just a few centimeters of disturbance in the open sea, they can grow large enough to cause real coastal damage. The event that triggered this Michi-tsunami happened thousands of kilometers away in the southwest Pacific Ocean. The Hunga-Tonga Hunga-Haipai eruptions on January 15, 2022 was absolutely massive. Some even describe it as the most powerful eruption since Krakatau. What's important here is that the eruption didn't just produce ash and tsunamis near the site. It also created atmospheric pressure waves called lump waves that travel across the globe at around 300 meters per second, almost the speed of sound. These waves interacted with the ocean surface and caused sea level disturbances in places as far away as the Indian Ocean. So let's take a closer look at this figure, which is key to understanding how the meteor-tsunami was detected. Panel A shows a map of the Indian Oceans with the locations of tide gauge, the red one, bottom pressure recorders or BPRs, the blue stars, and automatic weather stations, the green squares. This is basically the observations network that pick up the signals. Panel B is a zoom-in versions of the same map, and Panel C shows how the lump wave, the atmospheric pressure wave from the volcano, moves across the oceans. The colored contours represents the high and low pressure zones moving with time. Now, Panel D shows the most important data. The black line is the sea level from tide gauge, the green line is atmospheric pressure from the AWS, the blue line is sea level from the PPRs. What's striking here is that right after the lump wave passes, marked by the red vertical lines, sea levels begin oscillating. These oscillations persist for days, much longer than you expect from normal wave activity. So what this figure actually mean? These figures give us solid observational evidence of a meteor-tsunami. It shows the exact sequence. First, an atmospheric disturbance arrives and then the ocean responds, not with a single wave but with sustained sea level fluctuations. That's a key sign of meteor-tsunami, and it's how the researchers confirm that the events really happened and was linked to the eruption. Anup and his team found that the meteor-tsunami was observed across a network of tide gauge and bottom pressure recorders. The coastal stations recorded oscillations of up to 15 centimeters, which is significant especially when you consider that the open ocean signal was only a couple of centimeters. The amplification near the coast was up to 10 times higher. This is a classic signature of meteor-tsunami behavior. Small waves in deep water grow significantly when interacting with the shoreline. What makes this even more interesting is that the wave effects lasted for days, which is not usually the case with typical tsunamis that tend to decay more quickly. This persistence suggests complex dynamics like resonance and multiple refractions within semi-enclosed basins like the Bay of Bengal. Now, here's where we see the power of modeling. In Panel A, the color map shows the maximum simulated sea level change throughout the Indian Oceans after the eruptions. The yellow to red zones indicate higher amplitude, Panel B zooms into that regions, and Panel C gives us an even more detailed view of the Bay of Bengal. You can clearly see the western Bay of Bengal shows the largest sea level changes, matching what was observed in the real tide gauge data. Panels D through G shows Hogg-Muller diagram, which are time versus distance plots. They let us track how waves move across ocean cross-sections. These panels reveal the presence of force waves moving with the lump waves and free waves that appear later and move differently. Reflected and refractive waves also show up, especially near the coast. So this model successfully reproduced the Meteotsunami's behavior. It confirms that lump waves can generate real sea level impacts even far from the eruptions. More importantly, the model shows where and how much amplifications occurs, and that's critical for predicting future hazards in similar coastal regions. It also validates that the waves interact with bathymetry and coastlines in complex way, not just in straight lines. So, to better understand how meteotsunamis form, let's take a look at this simple figure on your right side. In the top part of the image, the shaded box represents the atmospheric pressure disturbance. This is the lump wave caused by the volcanic eruption. It's moving over the oceans at velocity v. While this pressure moves across the surface, it pushes the water beneath it, creating what's called a force wave. It is shown in the bottom part of the image. So, this force wave travels directly under the atmospheric pressure system. But when the pressure passes over a continental slope, something interesting happens. The force wave begins to separate from the pressure source and a free wave is generated. This free wave, leveled with C in the diagram, travels at the speed of a natural tsunami, which is slower than the lump wave. Now, here's why this matters. The free waves is where the amplifications occurs. As the water gets shallower near the coast, the free wave slows down and grows taller, a process called shoaling. These free waves combined with reflected and refracted components lead to high coastal sea level oscillations observed in the Indian Ocean. So, it shows the exact mechanism of wave transformations, from being forced by atmospheric pressure to becoming potentially destructive free wave. This concept is critical to predicting meteotsunamis, especially in areas with continental slopes and coastal shelves that allow these separations and amplifications to happen. So, what determines whether a meteotsunamis become dangerous? One key factor is bathymetry, the shape of the seafloor. Anup et al. Found that wave amplifications often occurred where water depths range from 200 to 600 meters, and where the bathymetry slope was just right. These conditions favor the separations of the wave and its transitions into a high amplitude free wave. In other words, the slope of the sea floors plays a huge role in deciding how much energy reaches the coast. This means local geography matters a lot. Some areas are just more vulnerable than others. These figures compare the meteotsunamis from the 2022 eruptions with two seismic tsunamis, the 2004 Indian Ocean tsunamis and one in 2012. Panel A shows the time series of sea levels at two tide gauge stations. You'll notice that the meteotsunamis lasted much longer. The oscillations didn't just disappear after a few hours, instead they persisted for 3 to 4 days. This kind of prolonged disturbance is unusual. Panel B shows the spectral energy, basically the frequencies or wave periods involved. Interestingly, all three events show similar peaks, suggesting that meteotsunamis can look very similar to seismic tsunamis in terms of wave behavior. Panel C provides a schematic diagram showing the propagation path of force and free waves along with reflected and refracted waves. The blue contours indicate areas where sea level rise was the highest. Panel D offers a conceptual snapshot of wave evolutions over time at 5 key stages. So, these figures tells us that meteotsunamis aren't just weaker cousins of seismic tsunamis. Their wave behavior, energy levels, and impact areas can be just as serious. It also shows that places affected by seismic tsunamis, like the Bay of Bengal, are just as vulnerable to meteotsunamis. So, early warning system can just look for earthquakes. They need to consider atmospheric and volcanic triggers too. To summarize, This was the first documented meteotsunamis in the Indian Ocean triggered by a volcano. The event was caused not by ground motion, but by a fast-moving land wave generated by the eruption. These wave interactions with the oceans and coastal features to create tsunami-like effect, amplified in specific region due to bathymetry. The research by Anup et al. 2024 not only shows the complexity of ocean atmospheric interactions, but also tells us that tsunami early warning system need to consider atmospheric triggers, not just seismic ones. And that's all. Thank you for listening.